Today, we're going to take a journey right into the mind of an AI to figure out how it actually makes sense of our world. Because you see, what's happening under the hood isn't reading, not in any way we understand it. It's something else entirely, something a lot more like interdimensional travel.
Let this idea sink in for a second, because it really changes everything. We think we're having a conversation, but from the AI's point of view, we're just feeding it a set of coordinates. It isn't processing language, it's performing computational geometry. Okay, so look at this. On the left, that's our world, right? We see a sentence. But on the right, that's the AI's world. Each of those words isn't a word at all. It's a precise point, a dot on a huge invisible map. And the meaning, well, that's all found in the distance and the direction between those dots. For an AI, language is literally a landscape.
So the big question is, how does this incredible translation even happen? How does a simple word get its own unique GPS coordinate in this universe of meaning?
Well, it's basically a two-step dance. First is tokenization. Just think of it like dicing vegetables. You're breaking down sentences into these smaller, manageable chunks. Then comes the magic part, embedding. Each one of those little tokens gets assigned a vector, which is just a fancy way of saying a very long list of numbers. And that vector is the whole shebang. It's the exact coordinate, the X marks the spot for that token on the map.
And this is where things get a little wild. This isn't just any map. So you have to wonder, why so complicated? Why not just use a simple 2- or 3-dimensional space? Well, you know, 2 dimensions are great for a treasure map. You've got length and width. Easy. But language is just infinitely more complex than a flat piece of paper. You can't capture all the nuance of a word like love with just an X and a Y coordinate.
Even 3 dimensions, the physical world we all live in, it's still not enough. Sure, adding that 3rd dimension gives us more room for complexity, but you'd still have different concepts crashing into each other. For the sheer complexity of language, we need to go bigger. Much, much bigger.
We are talking about thousands of dimensions. A typical model might use something like 4,096 dimensions to plot out all its concepts. And there's a really good reason for this massive scale. All those extra dimensions create so much space that every single idea can have its own unique neighborhood. It prevents concepts from overlapping. It's how an AI can tell the difference between bank as a place for money and bank as the side of a river.
So, once every word is a point on this ridiculously high-dimensional map, we can start to do some truly incredible things with what is, believe it or not, basically high school-level math.
The main tool here is something called cosine similarity. It sounds complicated, but all it does is measure the angle between the lines pointing to 2 different words. If the angle is really small, it means the words are pointing in roughly the same direction on the map. They're related, like cat and lion. If the angle is huge, they're unrelated, like cat and the moon. And this geometry lets AIs do something that is just remarkable: solve analogies with simple math. Look at this table. If you take the coordinate for king, then you subtract the coordinate for man, and then you add the coordinate for woman, you don't just land in some random empty space, you land on the exact coordinate for queen.
And this animation illustrates it perfectly. The relationship between man and woman is a specific vector. It's a direction and a distance. The AI learns that if you apply that same exact vector to the concept of king, you navigate through the space and land right on queen. It's analogical reasoning performed as simple arithmetic.
But hold on, there's a problem here. A word like bank has multiple meanings, but on a static map, it can only have one coordinate. This was a huge limitation for early models. How on earth can an AI understand context?
This problem has a name. It's called polysemy. How does a model know if the word light means not heavy, or if it means a source of illumination? The answer required a totally new kind of architecture.
And that solution was the transformer. Instead of a fixed printed map, the transformer creates a dynamic one. A word's coordinate is no longer a fixed destination. It's more like a starting point. Its final meaning gets determined by the gravitational pull of all the other words around it in the sentence.
This all happens through a mechanism called self-attention. The best way to picture it is that every word in a sentence is having a conversation. A word sends out a query, basically asking, hey, what kind of information do I need here? The other words offer up a key describing what they are. And if there's a match, the original word pulls in the value, the relevant information, and uses it to update its own position on the map in real time.
So this all builds to the absolute cutting edge of AI research.
Now that we know this geometric universe exists, scientists are trying to create a readable map of it, to actually see an AI's thoughts.
And this leads us to a pretty profound question. Can we find the exact vector, that one specific direction in this 4096-dimensional space, that corresponds to a single concept, something like the Golden Gate Bridge?
The answer, remarkably, is yes. Using a technique called a sparse autoencoder, which acts kind of like a prism, separating a jumbled beam of light into individual colors, researchers at Anthropic were able to untangle the millions of overlapping concepts inside Claude 3 Sonnet. And they successfully found individual features or directions that corresponded to very specific things, including one for the Golden Gate Bridge.
And to prove they'd really isolated this thought, they did something incredible called feature clamping. They essentially performed surgery on the model's mind. They artificially turned the dial for that Golden Gate Bridge feature all the way up, forcing the AI to constantly think about it, no matter what it was asked.
The results were just stunning. When they asked this modified AI about its identity, it replied, "I am the Golden Gate Bridge." It became completely obsessed, weaving the bridge into its answers about love, money, anything. This proved that an AI's behavior is a direct, steerable result of its journey through this vector space.
And this brings us to the crucial point. We can now actually start to visualize this entire universe. Using techniques that are kind of like what a cartographer uses to flatten a globe onto a page, we can project that 4096-dimensional space down onto a 2D map. And what emerges are these beautiful clusters of related ideas, forming entire galaxies of meaning, and making the invisible structure of an AI's knowledge visible for the very first time.
Which leaves us with one final, fascinating question to think about. If meaning truly is a map, are we simply explorers discovering a pre-existing mathematical structure that was always there in our language? Or, by defining the algorithms and feeding it the data, are we the ones drawing the map and defining the borders of what meaning itself can even be?